In this video, I want to talk about the idea of resonance. So in one sentence, the idea of resonance is that a system, whatever it is, has frequencies that it likes to oscillate at. And as a result, if you try to excite the system at that frequency, it's going to give you a bigger response than nearby frequencies. So our simplest system that exhibits resonance, we've actually already talked about, and that is our simple mass on a spring from our oscillations chapter. So here, we know that when left to its own devices, this object exhibits this oscillating behavior. And this oscillation always happens at a particular frequency that's determined by the value of the mass and the value of the spring constant, F equals 1 over 2 pi root k over m. But it turns out there is also something special about this frequency. And that is so I'm not going to pull the system and let it go on its own. I'm going to start it in equilibrium, and I'm going to move my hand up here, up and down just a tiny bit. So I'm just, as a reference, I'm moving it up and down less than a centimeter. But with a little bit of motion and then moving it at the right frequency, I can get this really big oscillation happening in my mass, even though I'm only moving my hand up and down a fraction of an inch. And that's because I'm moving my hand up and down a tiny bit at just the right resonant frequency to add energy to this system. So the idea that this resonance phenomena is if you're adding energy to the system at the right times, you can get this really big response for a small input. Okay, so this particular system only has one resonant frequency. And like I said, we know what that resonant frequency is. It's the same as the oscillation frequency. Systems with standing waves can have multiple resonant frequencies. And that's because, as we've seen, systems can have multiple standing wave patterns with different wavelengths that they like to be excited at. So there are multiple resonant frequencies. There are therefore multiple wavelengths that we'll say fit nicely into the system. We'll see some picture examples of what I mean by this in a little bit. All right, so let's talk about what this resonance looks like. And for determining what these resonant wavelengths and frequencies are, we need to know something about what's going on at the ends of our system, or what physicists call the boundary conditions. So in the case of our string stretched between 2 points, if we're looking at how this string is going to oscillate, it is going to do things differently if the two ends are fixed in place or if one end is free to move up and down. It turns out in the case of strings, it is practically, if you want to actually do this, it is much, much easier to fix the ends of the strings rather than to try to have a free string. So it's kind of hard to actually visualize what that would look like. But anyway, so imagine for a string where we have both ends fixed in place. That being fixed in place is affecting the standing waves that we can have on this string. So as we've seen, those standing waves have shapes that look like this. We'll draw a couple here. There's one that looks like this, and there's one that looks like this. So these are 3 different standing wave patterns on a string between 2 fixed points. So notice on all of these, the string at the very end is not moving up and down. So we have nodes on either end. So that's one example of what a boundary condition could be. In this case, our boundary conditions are both ends of the string are fixed. Really what this is saying is it's forcing the displacement of the string at the ends to be 0. So the same idea applies to systems other than strings, right? In the case of sound waves, we talked a little bit about sound wave reflection in a previous video. This is kind of like a hard wall for the sound wave to, run into and reflect off of. The wall does not allow the air to be displaced through the wall, right? It's a hard stop. So this string being fixed is kind of the equivalent of a solid wall for sound waves. We'll talk more about sound waves specifically later on. So for the case of these standing waves, let's look at what's going on here in these different cases. So this is all for the case of fixed end boundary conditions. So that is like a clamped string or a capped tube for sound waves. Okay, so let's say generically our system is size capital L, whatever that distance is. We could plug a number in, and let's look at what we know about this system. So we know that the distance between any two adjacent nodes is half a wavelength, lambda over 2. And we also know that for these three different modes, we have different wavelengths and therefore different frequencies. So each of these is going to have its own frequency and its own wavelength. So for this first one, which I'm going to label number 1, this distance between this node and this node, remember adjacent nodes is always half a wavelength, so that distance is lambda over 2. Conveniently, it turns out we know that this distance is also L, so lambda over 2 equals L. Or if we want to rearrange this, we get lambda equals 2L. I'm going to put a box around that, but I shouldn't box it. This is not like a fundamentally important equation. This is just for this thing. So, okay, so lambda equals 2L for this standing wave. For this next one, the system is still L, but now our wavelength is different. The distance between these two nodes, this is now our lambda over 2, our half wavelength, and this is half of L, right? We have one of these and another of these that add up to make L. So lambda over 2 is equal to L over 2, which means that lambda equals L for this standing wave. Here, between these two nodes, we still have a half wavelength. This is now 1, 2, 3. This is 1/3 of the length of our system. So this is 1/3 of L. Lambda over 2 equals L over 3. And so lambda equals 2L over 3. So we have 3 different values of the wavelength for these 3 possible standing waves. And we could keep drawing, we could keep drawing beyond this one, but I think this is enough on the board right now. These different modes have different names. It turns out this mode that we've drawn here is the mode with the longest wavelength. And as a result of that, because V equals F lambda for all waves, this is also the lowest frequency. This one is the next highest frequency and the second longest wavelength, the third longest wavelength and the third lowest frequency, and so on. So this mode here with the longest wavelength and the lowest frequency, this is called the fundamental mode, or the F is called the fundamental frequency. It is also sometimes called the first harmonic. I'm running out of space here. First harmonic. This one here is called the second harmonic. This one here is called the third harmonic, and so on. So from these lambda equations, so lambda of the fundamental mode is 2L, lambda of the second harmonic is L, lambda of the third harmonic is 2L over 3. There's something we can do to maybe make the pattern more obvious, and that is, instead of writing lambda equals L, I'm going to write lambda equals 2L over 2, which is of course equal to the same thing, right? I'm just multiplying by 2 halves. So we have 2L, 2L over 2, 2L over 3. So that gives us a very convenient equation to use. For the nth harmonic, lambda n, the wavelength of the nth harmonic, is equal to 2L over n. And now this is only true for a system with both ends fixed. So in the case of a string with both ends clamped, or in the case of a tube where we're looking for sound waves, a tube with both ends capped. So this equation is useful in these sorts of problems, but you should know that we never actually need to use it because we can always draw a picture or look at the pictures and figure out what's going on based on, this distance being lambda over 2, right? If we can draw this picture and know that this length is L and this length is lambda over 2, we can always get to this equation. So this is not, this may save some steps, but using these equations is never necessary. It's probably more useful in other circumstances to be comfortable with the standing wave diagrams and know how to get from these pictures to the equations rather than just using the equations blindly. That's my opinion of best practices in standing wave problems.